So now we are going into module 6.2. So module 6.2 is about cross-site request forgery. So in this again we go back to WASP top 10 of 2013 and we see that in number 8 is cross-site request forgery. So it's also a common one. So before we understand what happens in cross-site request forgery, let's talk about how the sessions are states are kept by using cookies. So remember that HTTP is actually a stateless protocol, and then so therefore when you log in and when you try to do something, go to a next page and so on, you have to re-authenticate yourself unless the system remembers who you are and the fact that you are authenticated. And therefore normally cookies are created by the server and sent to the browser with the reply of the original request, and in case of an authentication the authenticator cookie is kept. And then remember that because of the same origin principles, others should not be other tabs or where browsing that you are doing, that content should not be able to read this cookie or use this cookie. But when you now you are again interacting with the server, then the cookie is again sent and then the server doesn't have to re-authenticate you. So that's the idea. So here is a basic picture of how CSRF may happen. So suppose so there are two victims here. One is a user one user has to be victimized, and the site that you are targeting. Your main target is the site, but you have to use a victim user who has legitimate access to that site, and then you have an attack server. And so what you do is that suppose you have let's say this victim is your bank, so you connect to the bank, authenticate yourself, you have authenticator cookie and everything, and then you on another tab or another frame, you let's say advertisement frame on the side of your even in your bank website, you visit a site that has been compromised, and that site basically sends a malicious page to you, and that malicious page basically has code that basically sends a request from your browser to the target victim server, and that could actually be interpreted as your request by the server because it comes with your cookie, and so it's a cookie stealing, and then the server basically does whatever that forged request is asking it to do. It can transfer money to another account, for example. And this means that that's why many sites actually log you out after a little bit of timeout, because if you have an established session ongoing for a long time, your probability that some other site is going to compromise your browser and send a forged request through your session gets higher. So the question for you is that how long do you stay logged into Gmail and Facebook and so on? Usually those don't time out, and therefore being the carrier of a forged request to Gmail or Facebook could actually be a CSRF attack. So here is a more detailed account or detailed scenario. So user logs into, let's say, bank.com, session cookie remains in browser state. So the user visits another site which contains a form, and in that it basically saying the action is that go to the billpay.php on that bank site, and then whatever the name the recipient, the recipient is actually the bad guy, and then it basically scripts saying that document.f.submit. So this site sends you this code on your browser, and the browser sends the user authentication cookie with request, and the bank thinks that it is you doing a legitimate request for sending money to this or pay the bill for this bad guy. And so therefore it seems that one of the major problem why CSRF is able to do that is that the cookie authentication is insufficient when side effects occur, and the reason why the browser sent the authentication cookie for this is because the target site was the bank, and the cookie was specific to the bank, so therefore it got fooled into thinking that it should send the authentication cookie. So here is sort of like a message sequence chart for the same thing, that the victim browser goes to, let's say, to read a blog or something to the attacker's site. The attacker then sends this piece of code in which at the end there is a scripting that says you have to submit this form, and the target of the form is bank.com and so on. And the browser victim also does the same thing here, which is to go to the bank, and the referrer, when the browser is sending this cookie to the bank, the referrer field, if somebody checked, would be not the bank site, but rather the attacker.com, which is not common when you are doing monetary transaction. And if they check that, they would have figured out that this is a forged request. But if that was not checked, then only cookie is checked, then as far as cookie is concerned, it is the genuine cookie and the bank will fulfill the request. Now there is a cookieless example of CSRF, which is somebody might actually compromise the configuration of your home router and be able to control the home router. You already know that the home router is pretty easy to get into. Normally 192.168.1.0 or some fixed site address locally, that is the access to the configuration page of your home router, because your home router is actually running a web server and providing you the configuration page. So what may happen is that suppose you log into the home router, authenticate yourself, and you configure the router, and then at the same time you are visiting a bad website, and that sends you a malicious page, which is basically an HTTP. It's are properly designed so that it matches with the form fields for reconfiguring the router, and then it basically sends a forged request to the router and sets, let's say, changes the username, password, and since you are authenticated, and if the password change function of the router's web server is not rechecking the password by making you type it again, then it will basically allow it to change the password. But even if it doesn't change the password, it can change for example, the firewall configurations of your home router and things like that. In cyber security, sometimes people would say, like when you describe a scenario, people would say, oh, but no good engineer will do that, right? So for example, people would tell you that no good engineer will keep their password, the factory set password or the default password, and therefore changing the password through a CSRF is not possible, or things like that. But the fact is that most users of home routers are not engineers, or even if they are engineers, they are not security aware, and therefore through survey they found in 2007 that 50% of the home users have broadband routers with a default or no password. And this is not only for routers. We have seen this in the power grid. Like in power grid, many of the intelligent devices have passwords, but they are factory set password and nobody bothered to change them. And similarly, in the recent case of the Dyn attack, in October last year, if you remember, 100,000 IoT devices or Internet of Things devices like video cameras, webcams, and video recorders, they were used to launch a denial of service attack on the DNS domain server at the maintained by a company called Dyn, and that basically brought them down, and then therefore the internet was kind of not available in many parts in the US and later in Europe. So that basically shows that, and if you look at the code of the Mirai botnet malware, that basically were installed on these 100,000 devices, you will see that what the code does is it has a list of manufacturers and the name, the username, common usernames and passwords like root, and the password is root, or admin and the password is password, and things like that. And what this Mirai did is that it went through all these possibilities and then figured out how to take over the device. And many of these devices were very low cost device made in China, and they were actually not even having a facility for the users to change the password. It was kind of fixed. So it's not very uncommon for broadband routers and things like that to have factory set password because of the naivety of the user or negligence of the user. So in that case, what may happen is that what is called a drive-by farming. So user visits a malicious page, but fooled into visiting a malicious page and site, and the JavaScript script at the site scans the home network. Remember the image tag that was used for doing this before, and therefore once they find the home router, they actually log into the router and change the DNS entries in that server. And therefore, if let's say you have a local DNS on the home router which translates the your bank domain name to correct IP address. Now this malicious user might change it to its own IP, and then every time you type in bank.com, it takes you to his page, which is a fake website which looks very much like your bank, but it is not, and you type in login and password, and your login and password gets compromised. The other thing is that the routers, most of them are designed to actually take input from a send only HTTP message, which like HTTP post, and accept that and reprogram or reconfigure the router. So now, since CSRF has been there for a long time, since for about 15 years it is known, the credit card companies got fooled into revealing credit cards and so on. PayPal has been also victim, and various other sites. What people have looked at is how you can defend against CSRF attacks. So one of the major one is a secret validation token. So the every request is every time a request is made to the server, the validation token is generated, and the server has a way to validate that token, that it is indeed a token generated by the authenticated user on or his or her behalf, and therefore the forged request that is being generated from some kind of a code that you downloaded does not have access to that random number generator or whatever mechanism you have to create the secret validation token, and therefore it cannot pass the validation check on the server side, and therefore the forged request may be denied. Another thing is the referrer validation, which is we saw that in case of the HTTP, the message that was being sent, forged message that was being sent, there was a field in the header of the request which says referrer, and the referrer was attacker.com. So if somebody checked that the referrer is not the bank or some other known site, but it is some unknown site which is suspect, or sometimes they may be even blacklisted, then referrer validation can actually prevent the forged request from being executed. And then there is another one which is a custom HTTP header, and they basically create a custom header for a particular user, and that custom header has some amount of information that cannot be reproduced by the JavaScript or whatever has been brought into your system for a forged request. So forged request will not have the custom HTTP header, and therefore it will not be honored. So as I said, that the secret token validation is something that you accompany every request to the server, and it should be hard to guess, and it should be easy to verify on the other side, and usually it's a hash value of some kind from some random number generator, and the server side has a way to actually check that it is indeed created by the legitimate user. It could you could also use some of the other things like session identifier, session independent token, session dependent token, or HMAC of session identifier, and HMAC is the digest of the session identifier, and there are hundreds of literature, hundreds of papers on this, and which one works and under what corner cases it won't work, or how with a little more effort the attacker could actually steal some of this and use that with its forged request and so on. So we are not going into that kind of details here, just to give you an idea about what are the different defense mechanisms for this. So if you go to the site OWASP site and go into the CSRF prevention mechanisms, you can find a lot more gory details about that. So this is where if you look at the bottom of the screen, so you see that this one of the secret token example here. So now referrer validation is actually another way, and the idea here is that the referrer field in the header should be something that I trust. So if you ever get this Facebook login page and it's not located on the facebook.com, then you should not type in your password, for example. So therefore, if your Facebook login page opens in an iframe, it's hard to tell whether it's coming from Facebook, it is being hosted on facebook.com, and therefore you should not be typing in your password and so on. The idea is that if your referrer for these Facebook related forms is not facebook.com, if it is something else, then you should not trust it. If it is facebook.com, you can trust it, but many times the referrer field is omitted. It's not a mandatory field, and the reason is that many times the referrer field is even stripped, or sometimes if there are proxies, then the referrer field gets changed, and therefore there is no way to validate the origin. So then there may be another field created called original referrer, which basically keeps the original referrer even though it changes actual referrer due to the proxies. So it's a little bit a risky thing to depend solely on referrer validation. Now many times the policy of on the server is that it could be lenient referrer. So it means that it says that if the referrer is missing, then I assume that it is okay and I will take it. In case of strict referrer validation policy, you basically say that if the referrer is absent, I am not going to honor the request. Now in some cases, referrer also leads to a privacy sensitive information leakage. For example, if the referrer is an intranet site with a specific path, this competitors.html might be the page through which you have been referred, then having the referrer being sent, you are going to tell the other site, which may not be something under your control, that you have a competitor list and things like that in your intranet, and that may be a little bit problematic. So sometimes the organizations therefore strip the referrer information. Your local machine might be configured to do that. For HTTPS to HTTP transition, the browser might do that. User might actually put a preference in the browser for anonymity reasons, and then there could be buggy user agents. So therefore referrer may not always be possible there, and therefore if you are going to block all these possibilities, then you are going to be an useless site, because you are blocking everything, and that's why referrer validation could be a problem. So a broader view, so we saw that in CSRF examples like login CSRF or in case of banking CSRF, we saw what is happening is what we call a session riding. So you basically ride an existing ongoing session to send your request. So you don't, as an attacker, you don't have the credibility or authentication to go to those websites and do some action, but what you are doing is that you are fooling some other victim's browser to do it on your behalf by using the existing session. So it's called session riding. But there could be other reasons for or other things for which the cross-site request forgery might be used. So, you might want to export data from the user's browser to a server. You can disrupt the integrity of an user session. So, you might want the user to be caught by the server and blacklisted because the attacker knows that the server actually does a pretty strict CSRF checking, referrer validation or whatever, and then if you do this, then this user may actually get blocked. So, that could be another reason. Another could be that you want to get network connectivity on a network which requires authentication, or you want to read the browser state, or you want to write on the browser state. So CSRF could be used for such things as well. So this is another example where CSRF is used to embarrass people. So suppose you don't want your web search history to be known, or for example, if you are an activist and you are looking up literature on revolution or something, and you don't want the government to know that you are looking at such information, then what you could do is that what the government can actually do CSR, or the investigative agencies might do a CSRF, by which basically what it do is that it will make you go into a or somebody wants to frame you. So it might actually make you download this piece of code where you are actually going through an invisible frame, you are going into a bad website, and then that goes into your history of your browser, and then you could be implicated for visiting I don't know what terrorist website, bomb making website and things like that. So similarly, the payment login CSRF, so it happened in PayPal. So you actually make you log into PayPal, and then you basically mount a CSRF, so that your credit card that you have put in for the PayPal. So you make somebody log into your account and put in his credit card through CSRF. And login CSRF we already discussed. Now we already discussed this, that in some cases the sites redirect the browser to go to another site, and in that case the referrer validation doesn't work very well, and that is a problem that requires addressing, and for that custom header issues, custom header solution was considered. And so the recommendation for CSRF is that you should do strict referrer and origin header validation. So login form should be typically submitted over HTTPS, and HTTPS sites such as banking sites should use strict referrer origin validation to prevent CSRF. Now there are frameworks for web application design like Ruby on Rails that implements the secret token method correctly. So if you don't do secret method token method correctly, for example, if your random number generator is not biased, then you might actually be compromised. And so origin header is another way of looking at the referrer. Other referrer has a privacy problem, so you can look at other fields in the origin header. So in the next module we will do cross-site scripting. For today, these are the two modules for this week.